Hello friends, welcome back to my YouTube channel. This would be 18th part of my discussion on adsorption. I will continue discussing stage-wise adsorption, and in this video lecture I will be talking about multi-stage countercurrent adsorption. In coming few video lectures I will be talking more about multi-stage countercurrent adsorption. So let us begin the discussion. To start with, we will know few facts about the adsorption operation. It has a wide range of applications. Recovery of vapors from their dilute mixtures with gases, then solute recovery from liquid solutions, contaminant removal from liquid solutions, fractionation of gas mixtures where components in a gas mixture they are separated from each other. Then it is also used for fractionation of liquid solutions where components from the liquid solutions they are separated from each other. Both stage-wise and continuous contacting methods, they are in use in industrial applications. So in industrial adsorption, the two phases they could be contacted. Which two phases? The solid adsorbent phase and the fluid phase. They could be contacted in a stage-wise manner, or they could be contacted in a continuous manner. You can carry out the operation as a batch operation. So the adsorption operation, it could be a batch operation, or it could be a semi-batch operation, or it could be a continuous operation. Unlike other separation methods like distillation, liquid-liquid extraction, or gas absorption, adsorption is the only operation that can be carried out in a semi-batch manner. So how it is done? So in this case, the adsorbent it is confined to a fixed bed. The adsorbent it is confined to a fixed bed. So this would be the adsorbent bed, and the fluid phase it could be allowed to move continuously through this fixed adsorbent bed. So in this way you can carry out the operation in a semi-batch manner. So this is not possible with other separation methods. It is not possible with distillation. It is not possible with gas absorption. It is not possible with liquid-liquid extraction. It is only adsorption which could be carried out, or which can be carried out in a semi-batch manner. Now let us talk about stage-wise adsorption. So mostly the stage-wise operation it is employed to remove solutes from liquid solutions. So in this case, the two phases, the solid adsorbent phase and the liquid phase, they are contacted in stages, and each stage should have the following provisions. So it should have a provision for intimately contacting adsorbent and fluid phases for a sufficiently long time, and after a sufficiently long contact there should be a provision for physically separating the two phases. So each stage that is used in stage-wise adsorption, it should have a provision for intimately contacting the adsorbent and fluid phases for a sufficiently long time, and it should also have a provision for physically separating the two phases after they remain in contact for a sufficiently long time. So for batch operation, a typical stage would be formed in this way. There would be a agitated treating tank, and to this tank the feed solution is added, the adsorbent is added. They are intimately contacted with each other in this tank. They will remain in contact with each other for a sufficiently long time, and then for physical separation they will be taken to the resulting slurry. After sufficiently long contact, the resulting slurry slurry of solid adsorbent in the liquid solution, it would be taken out of the tank and sent to a filter press where the filtered solution will be separated from the solid cake. So this will be a cake of the adsorbent which has the adsorbed solute on its surface. Then the filtered solution which will contain the unrecovered solute in it, then it can be sent to the next stage. So for batch operations, this combination of the agitated treating tank and filter press, it forms one stage. So this combination will be acting as a stage. It will be acting as one stage in a batch operation. So this combination of agitated treating tank and the filter press, this combination forms one stage in a batch stage-wise operation. Let us move. So for multiple stages, you can have more combinations like this. Additional tanks and filters you can add as per requirement. So this combination can be repeated to have multiple stages. You can also carry out the operation in a continuous manner. But for doing that, the filter press that is used in batch operation, it has to be replaced with a centrifuge or with a continuous rotary filter. This is one thing. Or what you can do, the solid adsorbent phase, when the slurry comes out of the treating tank, the solid adsorbent phase, it can be allowed to settle. And how this can be done? This can be done by passing the slurry through a large tank. So when you are using a large tank, the slurry will get enough time, or slurry will remain in the tank for a sufficiently long time, during which the solid adsorbent phase, it can settle. And in this way, you can carry out the operation in a continuous manner. So in order to make the operation continuous, what is to be done? The filter press, it has to be replaced with either a centrifuge or with a continuous rotary filter. Or what you can do, in place of the filter press, you can use a large settling tank where the solid adsorbent phase, it will be continuously settled, and you'll be getting a continuous clear solution from the settling tank. So in this way, you can carry out the operation in a continuous way. So continuous operation, if you have to show it schematically, you can show it like this. So you have the agitated treating tank, a feed solution will be admitted to it, the adsorbent will be admitted to it. The resulting, after they remain in contact with each other for a sufficiently long time, the resulting slurry is removed out of the tank, and then it could be sent to a large settling tank where the solid adsorbent phase will settle. So you'll have settled solid adsorbent phase, and you'll have clear solution. Then you can remove the clear solution and send it to the next stage, and then you can separately remove the settled solid adsorbent phase. So in a typical continuous stage-wise operation, the combination of agitated treating tank or a agitated treating tank and a large settling tank, or a combination of agitated treating tank and a centrifuge, or a continuous rotary filter, this combination will form a single stage in a continuous operation. So I hope you have understood it. I have discussed it many times. I hope the concept is clear to you. If you have any doubts, you please mention them in the comment section. Now let us talk about multi-stage adsorption. So how this is carried out? Then to carry out it as a multi-stage operation, what you have to do, multiple stages are to be arranged in a cascade. Multiple stages are arranged in a cascade. What is a cascade? Cascade is an arrangement where multiple stages are arranged so that an output from one stage is an input to the next stage. So a cascade is an arrangement of stages in such a way that the output from one stage, let us consider this two stages. Feed is admitted to first stage, and then output from first stage is sent to the second stage as an input. So if the stages are arranged in this way, then what you have the cascade. So cascade is an arrangement of stages in such a way that output from one stage is input to the next stage. Then what are commonly used cascades in industrial applications? You have multistage cross-current cascade. I have completed my discussion on multistage cross-current cascade. And then you have multistage counter-current cascade, which I will be discussing in coming videos. So this will be an introduction to multistage counter-current cascade. So if you have to talk about multistage counter-current cascade, what can you say about it? The feed solution is admitted into the first stage. I'll shortly show you the schematic diagram. First, you just understand. In a typical multistage counter-current cascade, what is done? The feed solution is admitted into the first stage and the adsorbent is admitted into the last stage. So, whatever number of stages are there in the cascade, feed solution is admitted into the first stage, whereas the adsorbent phase, it is admitted into the last stage. And after they enter into the cascade, the solid and liquid phases, they will flow counter-current to each other through the cascade. So in this way, you have a counter-current flow of solid and liquid phases through multiple stages, and that's why we are calling the cascade as a multi-stage counter-current cascade. So I'll shortly show you the schematic diagram for a typical multi-stage counter-current cascade. So let us move ahead. So now let us look at n-stage counter-current adsorption, or let us understand n-stage counter-current adsorption. So this operation has n stages in it. So I'm calling it as n-stage counter-current adsorption. So it is carried out in a counter-current cascade where you have n number of stages. So a counter-current cascade containing n stages, the operation n-stage counter-current adsorption, it would be carried out in a counter-current cascade that is containing n stages. The operation is carried out in a continuous manner where the two phases, the solid adsorbent phase and the liquid phase, they are moving continuously from one stage to the other, but they are moving in a counter-current manner. Now let us look at the operation. The feed solution in this case, in our discussion, the feed solution would be a binary solution of A and B, two components, A and B. A is the solute that is to be adsorbed, and in our case we are going to assume that only A is strongly adsorbed. In other words, we are going to neglect adsorption of B. Adsorption of B is neglected. So we are calling B as the unadsorbed substance. The adsorbent phase that is used, first thing is it is not soluble in the feed solution. If you are using fresh adsorbent, it will not contain any solute on its surface. But if you are using a recovered adsorbent, then it will contain some solute on its surface. And in my discussion, I will be considering a recovered adsorbent. So it will be containing little amount of solute E on its surface. When we say that it is a recovered operation, that means it has been used in a previous operation for recovering E. And in order to use it for a fresh operation, if it is made ready, so in that process, some solute may remain on the surface of the adsorbent. So in my discussion, I will be considering a recovered adsorbent which will have little amount of E on its surface. So let me show the operation schematically. So this is stage number 1, this is stage number 2, and you have some more stages, and then finally you have the last stage in the cascade. This is stage number n. So as is done in counter current operation, feed is admitted to stage number 1. So feed will be identified by these parameters. Shortly I will tell you. I have discussed this in my earlier video lectures. I am giving link to the entire playlist of my video lectures on adsorption. It is in the description section. So feed solution, it is admitted to stage number 1, whereas and once it enters the stage, first stage, the solution will be moving from one stage to the other until it finally comes out of the last stage in the cascade, which is nth stage. Then the adsorbent phase, again I'll talk about this notations. That adsorbent phase, it is admitted into the last stage, and then it will be identified by these parameters. Shortly we will talk about them. And then the adsorbent phase will flow through various stages in the cascade. It will flow in a counter current manner. It will flow counter current to the flow of liquid phase, and that's why you have multi-stage counter current adsorption, where there are multiple stages in the cascade and the two phases, they are flowing in a counter current manner. They are flowing counter current to each other. So the adsorbent phase that comes out of the operation, it will be identified by these parameters. The liquid phases that come out of various stages, they will be identified by these parameters, whereas the adsorbent phase that comes out of various stages, it will be identified by these parameters. We are going to understand this. So let us talk about the inlet feed solution. Inlet feed solution L0, it is nothing but the total mass or total mass flow rate of the feed solution. It is total mass flow rate of the feed solution, mass per unit time, that is mass per unit time of A plus B, total mass. Then LS is the mass flow rate of the unadsorbed component. And which is the unadsorbed component in our discussion? It is component B. Then Y0 is nothing but wet fraction of solute A in the inlet feed solution. Then you have the inlet adsorbent phase. So in this case, yes, n plus 1 is the total mass flow rate of the adsorbent phase. So it is coming from a stage, a hypothetical stage after nth stage. So it would be n plus 1 stage. So accordingly, I have used this notation. So n plus 1 is total mass flow rate of the adsorbent phase that is entering into nth stage. So this, when I say total mass flow rate, it would be mass flow rate of solid adsorbent, which remains as it is, plus the solute on its surface. The amount of A changes as the adsorbent phase move through the cascade. Then you have SS, this is mass flow rate of the solid adsorbent, which is not moving anywhere. It will remain in the adsorbent phase. So SS is mass flow rate of the solid adsorbent, and Xn plus 1, you know, it is weight fraction of solute A in the entering adsorbent phase. Then, for outlet liquid solution, you have Ln. This is total mass flow rate of the liquid phase that comes out of stage number n. That is, it is mass flow rate of A plus B. Then you have LS, which is mass flow rate of the unadsorbed component, which is B. It remains unchanged. Whatever B enters into the operation, same amount is going to come out of the operation. Then you have Yn. It is weight fraction of the solute A in the solution that is coming out of stage number n. Then for outlet adsorbent phase, which comes out of stage number 1, so S1 is the total mass flow rate for the adsorbent phase, that is solid adsorbent plus adsorbed solute on its surface. Then SS is the mass flow rate of the solid adsorbent, which again remains same, unchanged. Whatever SS enters into the operation, whatever solid adsorbent it comes into N stage, the same amount of solid adsorbent it is going to get removed from stage number 1. It is only the solute in the adsorbent phase that will change. So that's why S1 changes, that is the total mass changes as you move from one stage to the other, whereas mass of the solid adsorbent, it remains same. Then X1 is weight fraction of the solute E in the outlet adsorbent phase, and then all L's, they represent liquid solutions, liquid flow rates. All S, they represent flow rates of solid adsorbent phase. So I hope the notations are clear to you, and now we are going to use these notations in our discussion. So what we will do, we are going to take material balance for the entire cascade, and for taking the material balance I am considering this envelope, the pink color envelope. So if you have to show the envelope separately, I can show it over here. If this block is representing the cascade, the envelope, then how many streams are associated with this envelope? You have the entering adsorbent phase, the entering feed solution, the solution, liquid solution that comes out of the operation, and the solid adsorbent phase that comes out of the operation. So you have this stream, you have this stream, you have this stream, and you have this stream. So for taking the material balance, we will be considering this envelope. So first we will take total material balance, and we are going to do that at steady state. So steady state total material balance, that is input is equal to output. So it would be L0 plus Sn plus 1 is equal to Ln plus S1. So that is input is equal to output. So total input material is equal to total output material. So that's why you have this equation, L0 plus Sn plus 1 is equal to Ln plus S1. Let us call it as equation 1. Then we can take solute material balance again at steady state. So it will be L0 Y0 plus Sn plus 1 into Xn plus 1, that is equal to Ln into Yn plus S1 into X1. So if you look at each term in the equation, so there is a product of total mass flow rate into fraction of solute. So total mass flow rate into fraction of solute in it will give you flow rate of the solute. So flow rate of the solute in the inlet feed plus flow rate of the solute in the inlet adsorbent is equal to flow rate of the solute in the outlet liquid solution plus flow rate of the solute in the outlet adsorbent phase. And I am calling this as equation number 2. Now the inlet solution, now our aim, as we did with the cross current operation, we are going to replace each term in equation number 2 with a term that will have capital Y, capital Y's and capital X in it. So we will analyze each of the term. So for example, let us start with the inlet feed solution. So the inlet feed solution, that is, we are talking about this. So it will be containing the solute to be adsorbed, and it will also contain B, which is the unadsorbed component. And if you have to express it mathematically, how can you express that? Let me erase it so that you'll understand it. So the inlet feed solution, the total mass flow rate of inlet feed solution is mass flow rate of A plus mass flow rate of B. So that is L0 is equal to mass flow rate of A is written as small y0 into L0 plus Ls. Then I will bring this term to this side. So it will be L0 minus y0 into L0, that is equal to Ls. And then I can take L0 common, so it will be L0 into 1 minus y0, that is equal to Ls. That is, L0 will be equal to 1 upon 1 minus y0 into Ls. And then I will multiply with y0 on both the sides. So it will be L0 into small y0 is equal to small y0 upon 1 minus small y0 into Ls. And then I can write the equation like L0 into small y0 is equal to capital Y0 into Ls, where capital Y0 is nothing but small y0 upon 1 minus y0. So this is weight fraction of the solute on solute-free basis in the inlet liquid solution. So this is basically capital Y0 is weight ratio, you can say. So this is mass of A in the inlet solution divided by mass of B. So that is nothing but capital Y0. So I have discussed it in detail in my earlier videos. All the link to the playlist, entire playlist is available in the description section. So the numerator, in the numerator you have mass of, you can show that it is mass of E, and in the denominator you can show that it is mass of V. So in the denominator there is no consideration of E, mass of E. So that's why we call it as weight fraction of E on E free basis in the inlet feed solution. Let us move ahead. Now let us analyze the inlet adsorbent phase. So inlet adsorbent phase, it is going to contain the solute because we are using a recovered adsorbent. That's why it will be containing little amount of E on its surface, and it will also contain the solid adsorbent. And if you have to express this mathematically, it will be written like this: Sn plus 1 is mass flow rate of E plus mass flow rate of solid adsorbent. That is, Sn plus 1 is equal to Xn plus 1 into Sn plus 1, which is nothing but mass flow rate of E, plus Ss, which is nothing but the mass flow rate of solid adsorbent. So let us simplify it. So that is Sn plus 1 minus Xn plus 1 into Sn plus 1 is equal to Ss. So this term is brought on this side. Then I can take Sn plus 1 common. So it will be Sn plus 1 into 1 minus Xn plus 1, that is equal to Ss. Then I will take this term to this side. So it will be Sn plus 1 is equal to 1 upon 1 minus Xn plus 1 into Ss. That is Sn plus 1 into, if I multiply with Xn plus 1 on both the sides, so it will be Xn plus 1 into Xn plus 1, that is equal to Xn plus 1 divided by 1 minus Xn plus 1 into Ss. And in the next step, I can introduce capital Xn plus 1, which is small xn plus 1 divided by 1 minus small xn plus 1. So finally you have this step: xn plus 1 into small xn plus 1 is capital Xn plus 1 into Ss. That is, in equation number 2, the term Sn plus 1 into Xn plus 1, it can be replaced with capital Xn plus 1 into Ss. Likewise, as per our earlier discussion, L0 into small y0, it can be replaced with capital Y0 into Ls. Okay, now for the outlet solution, it will contain A, which would be the solute that remains unadsorbed. Then it will contain B, the unadsorbed component. It will remain as it is. The quantity will remain same, quantity in the inlet solution and quantity in the outlet solution. Those quantities will be same. So mathematically it will be expressed as Ln is equal to mass flow rate of A plus mass flow rate of B. That is, Ln is equal to small yn into Ln plus Ls, because small yn into Ln is mass flow rate of E. So I will bring this term to this side. So it will be Ln minus yn into Ln is equal to Ls. Then Ln can be taken out as a common term. So it will be Ln into 1 minus yn, that is equal to Ls. Then this term I can bring on this side. So it will be Ln is equal to 1 upon 1 minus small yn, that is into Ls. Then on both the sides I will multiply with small yn. So it will be ln into small yn, that is equal to small yn divided by 1 minus small yn into ls, and then small yn upon 1 minus small yn is nothing but capital Yn. So therefore you have this equation, ln into small yn, that is equal to capital Yn into ls. So in this case, capital Yn is small yn upon 1 minus yn. That is, the term ln into yn that is present in equation number 2, it can be replaced with the term capital Yn into ls. Now for the outlet adsorbent phase, it will contain A, which would be the adsorbed solute, and then it will contain the solid adsorbent, which has remained unchanged. So mathematically this will be expressed as S1 is equal to mass flow rate of A plus mass flow rate of solid adsorbent. That is, S1 will be equal to X1 into S1 plus SS. So that is, I can bring this term on this side. So it will be S1 minus X1 into S1, that is equal to SS. And then S1 can be taken out as a common term. So it will be S1 into 1 minus X1, that is equal to SS. And that is, S1 will be equal to 1 upon 1 minus small x1 into SS. That is S1. If I multiply with small x1 on both the sides, so it would be S1 into small x1, that is equal to small x1 upon 1 minus small x1 into SS. And then small x1 upon 1 minus small x1 is capital X1. So we will have S1 into x1, that is equal to capital X1 into SS, which in this case, as we understood, capital X1 is small x1 upon 1 minus x1. That is, we can replace the term x1 into S1 into x1 with this term capital X1 into SS. So after we have all replacements ready with us, we are going to replace all the terms in equation number 2. So we have equation number 2. What is that equation? L0 into small y0 plus Sn plus 1 into small xn plus 1, that is equal to Ln into small yn plus S1 into small x1. Now we are going to replace all these terms. How? L0 into small y0, it can be replaced with capital Y0 into Ls. Sn plus 1 into small yn plus 1, it can be replaced with capital Yn plus 1 into Ss. Ln into small yn, it can be replaced with capital Yn into Ls. And finally, S1 into small x1, it can be replaced with capital X1 into Ss. So let us do the replacement. So if you use all this in equation number 2, we will have Y0, capital Y0 into Ls plus Xn plus 1 into Ss, that is equal to capital Yn into Ls plus capital X1 into Ss. Then let us have all Ls terms on one side. So it will be capital Y0 into Ls minus capital Yn into Ls, that is equal to capital X1 into Ss minus capital Xn plus 1 into Ss. And then you can take Ls common on this side, so it will be capital Y0 minus capital Yn into Ls, that is equal to capital X1 minus capital Xn plus 1 to Ss. And then you can rearrange it in this way: capital Y0 minus capital Yn divided by X1 minus capital X1 minus capital Xn plus 1, that is equal to Ss plus Ss upon Ls, and I am calling it as equation number 3. So every term Y0 minus Yn, it will be positive. X1, that is the final concentration of the adsorbent that comes out, minus concentration of the solute on the adsorbent that comes out, minus concentration of the solute on the adsorbent that enters. So that's why it will be, there is no need of making any rearrangement as we did with the cross current operation. So the equation will remain as it is. And equation number 3, what you can say about that equation? So it represents a straight line on a xy plot, which is nothing but the equilibrium diagram. And the line which we are talking about, it passes through 2 points, which are these 2 points, capital X1 Y0 and capital Xn plus 1 capital Yn, and this is nothing but the operating line for the n stage counter current adsorption operation. So it has a slope of SS by Ls, which is positive. So it has a slope of SS upon Ls. If you remember, the slope of the operating line in cross current operation, it was negative, but for the counter current operation, the slope is positive. So in this way, we get the equation for the operating line for the n stage counter current adsorption operation. So after getting the equation for the operating line, now let us plot the operating line on the equilibrium diagram. So the equilibrium diagram, as you know, it is a plot of capital X on the x-axis and capital Y on the y-axis. And when you plot the equilibrium values, you are going to get a curve which is the equilibrium curve. Now in the operation, if I can show that operation by a rectangular box, then the feed solution is entering into the operation. This rectangular block has the n stages in the cascade. So entering liquid, it has a concentration of capital Y0, and when it comes out, the concentration of the solute in the liquid solution, it is Yn. And if you have to show that, that means in the liquid phase, the concentration is changing from Y0 to Yn. And to tell you the fact that since solute is getting adsorbed, concentration of the solute in the liquid solution, it should decrease from Y0 to Yn. And you can show that on this diagram. So concentration of the solute in the liquid solution, it decreases from Y0 to Yn. Whereas for the adsorbent phase, the entering adsorbent phase, it has a concentration of capital X n plus 1, and as it moves through the cascade, solute gets adsorbed on its surface. Therefore, the concentration of the solute on the surface of the adsorbent, it increases as the adsorbent phase moves through the cascade. And when the adsorbent phase comes out of the operation, the concentration on the surface of the adsorbent is X1. So that means in the case of adsorbent phase, concentration of solute increases from Xn plus 1 to X1. So you can show on this equilibrium diagram. So it increases from Xn plus 1 to X1. Now let us look at 2 points. One is this point, which has coordinates of X1 and Y0, and there is another point which has coordinates of Xn plus 1 and Yn. So one point is this point, I am calling that as point P, and the other point is this point, I am denoting that point by Q. It has coordinates of Xn plus 1 Yn. Point P has coordinates of X1 Y0. So in this way, we have located the 2 points. Now, if you look at point P, say the coordinates of point P are X1, Y0. That means point P is representing this end of the cascade. So this end of the cascade is represented by point P, whereas this end, it is represented by point Q. You need to understand that. Point P represents the left end of the cascade, whereas point Q represents the right end of the cascade. Point P, it represents the left end of the cascade, and point Q, it represents the right end of the cascade. I hope you are understanding the concept. If you have any doubts, you can mention them in the comment section. So let us move ahead. Now, first of all, I will rub this because we will not need it anymore. Okay, so then the line connecting points P and Q is the operating line for N stage counter current adsorption operation. So point P with coordinates x1, y0, it represents the left end of the cascade. I have talked about it. And then point Q with coordinates capital Xn plus 1, Yn, it represents the right end of the cascade. And the line PQ is the operating line. So I hope you now know how to plot the operating line on a typical equilibrium diagram. Let us move ahead. Then we will know how to plot the number of theoretical stages, and we are going to do that on the equilibrium diagram. So you have the equilibrium curve and then the operating line. The theoretical stages will be plotted or will be drawn between the operating line and the equilibrium curve. So you are going to start at point P, travel vertically to reach the equilibrium curve. Once you reach the equilibrium curve, you will be traveling horizontally to reach the operating line, then vertically to the equilibrium curve, horizontally to the operating line, vertically to the equilibrium curve, and finally horizontally to the operating line. So in this way, you can represent, or you can draw the number of stages that are present in the counter current cascade. So in this case, this is just for your understanding. Now, if you try to count the number of stages for this diagram, you will come to know that there are 3 stages. So 1, 2, and 3. So like this, you have to plot these triangles and then count the number of triangles. The number of triangles will be the number of theoretical stages in the counter current cascade. But let me tell you, as was the case with cross current operation, multi-stage cross current operation, if you go beyond 2 stages, the operation will not be economical, because beyond 2 stages, the cost of physically separating the 2 phases, it increases. So even in the case of multi-stage counter current adsorption, if you go beyond 2 stages, the operation will not be economical. So you have to keep this thing in mind. Let us move ahead. Then there is another concept. What is that? The concept of minimum adsorbent to solvent ratio. So that means it is the operating line which has a slope of SS minimum by LS, where you have the minimum value for the slope. So this is called minimum adsorbent to solvent ratio. SS minimum by LS. We are going to denote that as SS minimum by LS. Now the solvent in this case, for this particular case, solvent, what is solvent? Solvent is nothing but the unadsorbed component. And in our discussion, we have considered a binary mixture of A and B, in which B is the unadsorbed component. Therefore, for our discussion, or in this case, the solvent that we are referring to, he is nothing but the unadsorbed component in the feed solution. So SS minimum by LS this ratio, minimum adsorbent to solvent ratio, it corresponds to the largest slope of a operating line that touches the equilibrium curve within the specified concentration range. So here SS minimum by LS is the largest slope of a operating line that touches the equilibrium curve within the specified concentration range. So here we are talking about those operating lines which touch the equilibrium curve. And out of all these operating lines, we are concerned with a operating line that has the largest slope among them. The largest slope of all the operating lines that touches the largest slope for the operating lines that touches the equilibrium curve within the specified concentration range is the minimum adsorbent to solvent ratio. Minimum adsorbent to solvent ratio. So I hope you are understanding this. So if somebody asks you to define minimum adsorbent to solvent ratio, how can you define? You can define it as the largest slope of a operating line that touches the equilibrium curve within the specified concentration range. And the point at which the operating line touches the equilibrium curve, that point is called the pinch point. The point at which the above operating line, it touches the which operating line? The operating line that has the largest slope. That has the largest slope and it touches the equilibrium curve. So the point at which the above operating line touches the equilibrium curve, it is called the pinch point. And the location of the pinch point, you need to locate the pinch point in order to find the minimum adsorbent to solvent ratio. So the location of pinch point, it depends on the nature of the equilibrium curve. I will talk about it. So when the equilibrium curve is a straight line or concave upward, if the equilibrium curve is almost a straight line or it is concave upward, I will show that. The pinch point occurs at the concentrated end of the cascade, which is the left end of the cascade, left side of the cascade. So again, if you look at the diagram, you have the cascade. Let me use this rectangle to represent the cascade. So this is the left end, this is the right end. So at this end you have feed solution which is concentrated, and as it moves it becomes dilute, and the other phase is the adsorbent phase which has adsorbed solute on its surface. So here this concentration of solute is more. Concentration of the solute on the adsorbent surface, it is more. So left side is again it is said to be the concentrated end of the cascade. It is said to be the concentrated end of the cascade. So one case is the equilibrium curve could be a straight line or concave upward, and if that is the case, the pinch point will occur at the concentrated end of the cascade. So what are the coordinates for at this end? You have for the liquid solution, you have y0, and for the adsorbent phase, the concentration is x1. So if you remember, this coordinates, point P has this coordinates. So in this case, pinch point will occur at point P when if the equilibrium curve is a straight line or it is concave upward. Then let me erase it. When the equilibrium curve is concave downward, the pinch may occur at the point of tangency. So if the equilibrium curve is concave downward, then the operating line with largest slope that touches the equilibrium curve, it would be a tangent. And in that case, the pinch point would be the point of tangency. I will show you how the pinch point is located after this. I hope you have understood what is minimum adsorbent to solvent ratio. it is the largest slope of a operating line that touches the equilibrium curve within the specified concentration range. The meaning is there may be multiple operating lines that will touch multiple operating lines that may be touching the equilibrium curve. Out of this multiple operating lines, we are talking about the operating line that has the largest slope. And it touches the equilibrium curve. So slope of such a operating line is nothing but the minimum adsorbent to solvent ratio. So I hope you have understood the concept. Now we will show how the pinch point is located in the two cases. Okay, now let us know how to locate the pinch point if the equilibrium curve is a straight line. So I will show that. So you have the equilibrium curve. Now the equilibrium curve is a straight line. Then you have the 2 points. The operating line will start at point Q, and then it will touch the equilibrium curve at the other end, at the left end or concentrated end of the equilibrium curve. So this is, if you remember, this is point Q and this is point P. So when the equilibrium curve is a straight line, point P will be the pinch point. Point P, it has coordinates of x1, y0, which represents the left end of the cascade or the concentrated end of the cascade. So if the equilibrium curve is a straight line, then pinch point will be located. The point where the operating line touches the equilibrium curve, the pinch point, it will be located in this way. Then if the equilibrium curve is concave upward, then again the same thing. The pinch point will occur at the concentrated end. So you have point Q. You have point Q over here, and the pinch point will occur at the concentrated end, which is point P, which has coordinates of y0 and x1, y0. So pinch point, again, it occurs at the concentrated end of the cascade. So this is how you can draw the operating line and locate the pinch point. If the equilibrium curve is a straight line, pinch point will be located at the concentrated end, or on this diagram it will be located at the top. And even if the equilibrium curve is concave upward, even then the pinch point will be located at the top. Then finally, we will look. Okay, now let us know how to locate the pinch point if the equilibrium curve is concave downwards. So you have the equilibrium curve, and if the equilibrium curve is concave downward, then the operating line or pinch point will be located in this way. So you have point Q over here, and then if you draw a line that touches the equilibrium curve, the pinch point will be occurring at the point of tangency. And you have point P that will be located over here. So this is point P, this is point Q, and this is the point of pinch point, the point of tangency. Pinch point. This is the pinch point. So in this way, pinch point will be located if the equilibrium curve is concave downward. So depending on whether the equilibrium curve is a straight line or it is concave upward or it is concave downward, the location of the pinch point will change. So the nature of the equilibrium curve is important in this case. So all that you have to do is you have to draw this line, the line that is touching the equilibrium curve and has the largest slope. Find the slope of the line. Slope of the line is nothing but the minimum adsorbent to solvent ratio. I will be solving some numericals that will tell you how to get the minimum adsorbent to solvent ratio. In my coming videos, I will solve few numericals on that. Okay, so as the number of stages is increased in the cascade, what happens? The quantity of adsorbent required, it decreases. It decreases rapidly first, and then it approaches the minimum value only asymptotically. So you can understand this with the help of this graph. So if you just plot the quantity of adsorbent versus number of stages. So as you increase the number of stages, the quantity of adsorbent will decrease. It will decrease rapidly initially, and then it will approach the minimum value only asymptotically. So you need to understand that. So therefore, in actual practical applications, what is done? We need to separate the two phases. An intermediate separation of solid and liquid phases, it must be made between the two stages, and that involves cost. And if you increase the number of stages, the cost of separation is going to increase. And therefore, it is rarely economical to use more than 2 stages in the cascade. Same was the case with cross-current operation. If you try to use more than 2 stages, the operation may not remain economical. So, same is the case with counter-current operation. What is the reason for that? The reason is the cost of physical separation. It will increase if the number of stages increases, and if the number goes beyond 2, then the operation may not remain economical. So with this, I will end my discussion for this topic. Here I have discussed multi-stage counter-current adsorption operation. I have discussed how to write material balance for a typical counter-current cascade containing n number of stages. Then how to get the equation of the operating line, how to plot the operating line on the equilibrium diagram. Then I have discussed the concept of minimum adsorbent to solvent ratio. What is pinch point, how to locate it for different types of equilibrium curve, how to locate it if the equilibrium curve is a straight line, if it is concave upward, if it is concave downward. So I hope you must have understood what I have discussed in this video lecture. In my coming videos, I will be discussing few numericals based on multi-stage counter-current adsorption. So I will end my discussion for this lecture. So thanks for watching my video lecture. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you will be notified as soon as I upload any new video on my YouTube channel. For now, have a nice day and hope to see you soon in my next video lecture. Have a nice day. Take care. Bye-bye.